Now that we've gone through an introduction to probability, we can move on to explaining and exploring different probability distributions. The most important part to probability distributions is knowing the differences between discrete and continuous types of variables, and to know which types of distributions apply to which types of random variables. So the goals for this chapter are to define random variables and different classes of those random variables, and then define the different characteristics of discrete versus continuous probability distributions. Once we know that, we can then take a look at different types of discrete and continuous distributions and some probability functions for each. Now, for this chapter, we will be going through Python code. There's a lot more examples in the workbooks, but this should give you a good visual overview of the different types of packages to use, as well as what types of graphs we'll be looking for and applying when we've decided which probability distribution to model after. But before we talk about anything, we have to talk about something called the random variable. So there are discrete versus continuous variables. We already learned that in a previous chapter, but now we have to introduce something called a random variable. So we're going to call X a random variable, and it's called X because we do a lot of experiments, and when we're doing an experiment on something, then we call that something a random variable because we're still trying to learn something about it. So X is a random variable that represents any variable that varies or changes depending on the outcome of the experiment being measured. Now, if the possible outcomes are listed out using whole numbers, they're going to be discrete random variables. And based on just the discrete nature of those variables, you can either have a small list that's easily countable, we call that a finite discrete random variable, or you may have just too many possibilities to count. Even though it's still whole numbers, you can have countably infinite discrete random variables, which means that your number ranges from 0 to something very, very large, and you just don't want to waste time listing them all out. Now, in that case, what happens if your data set truly is infinite? So if the possible outcomes can be described using an interval of real numbers and can be modeled by a continuous function, then we call that a continuous random variable. In these cases, these variables are going to be uncountably infinite. So there are too many possible values to list or count, but there's a very, very high level of accuracy and precision when we measure those values. So now our question is going to be, what kind of distributions are possible with each? Before we get to that, I want to go back to the Bayesian versus frequentist views of probability. The frequentist approach to probability allows us to interpret probability as a long-run frequency. So the goal is to create procedures with some guarantee of frequency. So parameters are going to be fixed constants, and the probability statements are usually about procedures so that you can fix something every time you do it. Now, the Bayesian approach to probability is a little bit different. The probabilities are interpreted as subjective degrees of belief. So the goal is to state and analyze those beliefs, and that fits very well with the scientific method. Parameters must be random variables because we're forming a hypothesis about something that's changing. And probability statements are then going to be about those parameters. Here, we're supposed to choose a probability density called the prior distribution that expresses our beliefs about the parameter before we see any data. Then we can choose a statistical model that reflects our beliefs about the data that's given prior to us. And after observing all the data that we've collected, we can update our belief and we can calculate a posterior distribution to further analyze the statistics. So these are the steps that we'll take in later chapters when we're actually doing statistical analysis, but that's kind of what we're leading up to. So let's start off with discrete probability distributions and probability mass functions. The three main types of distributions you'll have to know of are uniform, binomial, and Poisson. It's the two last ones that are the most important. So what is a probability distribution? It's basically a mathematical function that gives the probabilities of occurrence of different possible outcomes of an experiment. So when we're looking at a discrete probability distribution, we use P of x as the probability of each value of x for a random variable, capital X. Now, there are different types of probability distributions and functions depending on what your random variable is. So we want to take a look at the probability mass function, and that gives the probability that a discrete random variable is exactly equal to some value, especially because you only have integer values here. When we take a look at probability density functions, we call that a PDF, and that gives the probability that a continuous random variable falls within a particular range of values. So instead of saying, what's the probability of x equals a? We usually say for a probability density function, what are the chances, or what is the probability that x is between a and b, or x is greater than a, or x is less than b? You're usually looking at a range of values because each individual data point is so highly precise and accurate that the only thing you can really predict is the probability of a range of values happening. So if you have a PDF, because it is a continuous curve, you can take the integral to get the area underneath the density function to get your positive area and therefore your probability of that range taking place. Some common characteristics of probability functions, whether it's the mass or a density function, first, all the probabilities will have to add up to 1. Next, individual probabilities have to be between 0 and 1. So that makes sense. It's the same concept from before with our counting statistics. So we can now move on. There is one more function I want to talk about, and it's the cumulative distribution function. That CDF is going to provide the probability that x takes on a value less than or equal to x. So this is very useful in calculating probability within a range, and we usually use that with the probability density function. So if I want to calculate the probability of an event taking place between A and B, then I am going to calculate the CDF of B, which gives me the area from -infinity to B, the probability of that, and I'm going to subtract the probability of -infinity up to A, and that gives me the probability between A and B. So that's when the CDF comes in handy. So now let's take a look at the discrete uniform probability distribution. That distribution is the easiest to look at. It's basically got a flat top. The distribution is when the PMF is a constant value. Every single value has an equal chance of taking place. Basically like a coin toss, rolling a die, things like that. So P of x is equal to 1 over n, with n being the total number of possible events that can take place. If I'm rolling a die, then I have 6 different faces, and I have 1 out of 6 chance of getting each one. So how can I create this graph or this histogram? We can set our first value and our last value to be 1 and 6. I'm going to say x is equal to a range of values from a to 6, inclusive, because I add the +1. Then I'm going to generate random values from 1 to 6, but I use rand_int from SciPy_stats, and that gives me random integer values from a to b. Then what I'll do is create a variable over here, and I'm going to say that for each of these values, I'm going to calculate the probability of those values. So I have discrete uniform dist for this one, the distribution. I use the PMF function of x for each of these. And so the probability of getting 1 is this, the probability of getting 2 is this, so on and so forth. And then I can plot the bar graph and then show it after. So take home message from here, whether you're using a uniform, exponential, normal, any type of, not normal, whether you're using a uniform or binomial or Poisson distribution, anything that's discrete, the PMF function is going to calculate the probability mass function for a specific x value or for a specific range of x values. So that's the important one to remember. This one right here. Next, we can move on to the binomial probability distribution. The binomial distribution is very simple. It's a distribution where you have n identical trials, each with only one of two possible outcomes. When we have two possible outcomes, we simply say one is successful, one is a failure. So we call the successful variable p, or successful probability p, and we call the probability of failure q, which is equal to 1 minus p. The values of p and q must be consistent from trial to trial because the trials are independent. So based on that, if we do have a binomial experiment, we can use the binomial equation to calculate the binomial probability distribution. So I have it presented here. Do you have to remember it, and do you have to do it from scratch? From Python coding, I would say not so much. Let's take advantage of what's given to us already. We can use the binomial function or the binomial package from scipy.stats. And how do we use it? Given n trials with a probability of success p being 70% or 0.7, we can define them as n equals 15 for just a random number of trials. You can do whatever you want. And p is equal to 0.7. Now, the x values is going to be a list from a range of n plus 1. So you're going from all the values from 0 to n plus 1. So you have something like this. I'm now going to call a new variable, define a new variable called binomial PMF for the probability mass function. And this is just, I presented this in square brackets to show you a different way of calculating the PMF for a list of values. So in here, I have brackets. I'm going to calculate binomial.pmf of x for n trials with the probability of success p for all of the x values in this list. So that's just another way of getting all the PMF values for all your x values. And then you can plot your bar graph. You have x values as well as a list of all the corresponding PMF values for each of these. So based on this, you get a distribution. Looks like a binomial distribution. From there, you can also do you can add in several more functions. You can calculate the mean by using dot mean. You can calculate the variance, and you can calculate the standard deviation for different numerical measures. So those are things that you can just use for assignments, for workbooks, and even in the future in your studies to quickly calculate numerical measures for a distribution. If you want the individual equations, you can take a look in the workbook. Okay, now for the Poisson probability distribution. Essentially, the Poisson distribution is very, very useful if you have something that takes place over a certain period of time, and that one thing that takes place happens an average number of times. So we define it as a distribution for events that occur an average mu number of times over a certain period of time or space. We call k one occurrence of that event. So events have to occur randomly, and they must be independent of one another. The distribution is defined as the probability of x equals k. So let's say 4 occurrences taking place out of all this is equal to this equation. Once again, do we need to know how to do this math by hand? I would say no. Let's take a look and go through how we can apply Python code to this distribution. So we can use Poisson, the Poisson package from scipy.stats. We have a few different variables or parameters to define. With the Poisson probability distribution, we now have an average. So we need to define mu, and let's just say it's equal to 4. We then have to set our x-axis. So we have a range of values, let's say from 0 to 10 for the number of events we want to test. And we're going to use half steps from for each of these. Now, we then create a variable called Poisson PMF so that we can calculate all of the probabilities from the probability mass function for all of our x values. Now it's very simple. You use Poisson.pmf and then you use for all x values, and also given that the average is mu. So based on that, you can plot all of your values and you get your Poisson distribution for mu equals 4. Okay, so apart from that, you can also use mean, variance, and standard for your numerical measures. But another take-home message from this slide is that you can simply use Poisson.stats to get what we call the first 4 moments of the function. That gives you your mean, your variance, your skew, and your kurtosis. So we won't be talking about the moments until a later chapter, but you can use the stats function to quickly grab all 4 of these in an array so that you can present them very easily in the future. Oops. So when do you want to use each distribution? Let's go through 2 examples from a previous class that you probably have taken before. So first example, there are a total of 24 lectures in the term and 100 students. The prof randomly selects a student to ask questions each lecture. What is the probability that the same student will be asked twice in the term? Well, over here you have, we're being asked about a probability. We're going to have to assign a distribution. We do have discrete variables here because we have the selection of students. You can't have half a student or half a selection. So the discrete variable means that we can either have uniform, binomial, or Poisson distributions. Looking at this, we ask ourselves, are the chances of getting picked equal each time? Probably not. We don't have a uniform distribution. Is there a rate to this? I read this and it's asking me, what is the probability that the same student will be asked twice in the term? This really isn't a rate. It's more of 2 questions being asked to that one student. So with a chance of success being 1 out of 100 students and a total of 24 trials, that gives me a binomial distribution. So we have n equals 24 lectures, k equals to 2 questions for that student, and a chance of being successful 1 out of 100 each time. So how can we calculate this? We can simply import binomial function or the binomial package from SciPy stats. We define each of these values. N is 24, k is 2, and p is 0.01. And we're going to print there is a binomial.pmf of k and p in that specific order, because that's the definition of their parameters. And then you multiply by 100 to get the percent. So after that, you get there is a 2.2% chance that the same student will be asked twice in the term. So that is the proper answer, better than you doing all the math yourself. Next example, we have 150 Canadian geese fly by the University of Waterloo every 10 days. What is the probability of having 5 Canadian geese fly by in one day? Now, this gives me a rate. It's not a rate that I'm trying to find like the previous one where I'm trying to figure out the probability of something happening twice. I'm already given a rate over here. 150 Canadian geese fly by the university every 10 days. So if I want to figure out the number of geese per day, I can just divide the 2 of them and I get an average number of 15 geese per day. And that we want to be able to figure out how many, the probability of 5 geese flying by in one day. So we're going to use the Poisson function from scipy.stats. We define mu, we define k as 15 and 5 respectively. And then we just use the PMF function with k and mu. And I specifically have these reversed to let you know that I didn't do this on purpose. There is a specific order for your PMF functions. So make sure that before you use these functions, take a look at the documentation if you forget, and make sure you're putting the values in the correct location so that the math works out correctly. So I'm multiplying that by 100 and I get 0.19% that 5 geese will fly by within 1 day. So now let's talk about continuous probability distributions, and specifically probability density functions, which are used for continuous distributions. There's essentially one really important distribution we have to go through, but we are going to go through uniform and exponential probability distributions first, and then go through the normal or Gaussian probability distribution. Okay, so with continuous variables, our probabilities now fall within intervals or values. For example, what is the probability that a random value variable x falls into an interval between a and b? So we use a probability density function that's described by a mathematical formula, f of x, to represent these continuous distributions. Now, the area underneath the curve, so let's just take a look at this curve over here. The area underneath is depicted in red. There's going to be a probability underneath this region, and that's the probability that x is going to fall within that interval. So in order to get the area underneath the curve, we can simply integrate, and then the area under that entire distribution from start to finish must be 1, just like with the probability mass functions. And this whole thing would be called the total area would be called the total probability. So to calculate the probability between two values a and b, we would, number 1, either apply the CDF function, the cumulative distribution function, and we're going to find the probability as CDF of b minus CDF of a. So if this were CDF of b, it would be the full area from the beginning to point B, and then CDF of A would be the area from here to A. If you subtract the two, the difference will be the red area over here. So that's where that CDF function comes in handy. For specific values, we can use the PDF function to get a specific probability for a small range of values. So let's take a look at the uniform versus the exponential probability distributions. The uniform continuous probability distribution is essentially just a constant function. If c is a constant, then the PDF is given by f of x is equal to c, and you basically get a straight line. If you want to draw out this straight line, you can always import the uniform package from scipy.stats. And you can essentially just create all of your x values from the uniform distribution. I want to say PPF over here represents the percentage point function. It's very useful if you want to plot something from the beginning of the probability distribution to the end of the probability distribution. It's essentially like a percentile, and the PPF is defined as the inverse of the CDF. So we omit the end points, the start and the finish of 0 and 1, to prevent dividing by 0. So once you have that, you can divide it by however many data points you want to create your x values. And then to get your actual density values, you can use uniform.pdf of all of the x values you've just created in your list to plot a point or to plot a line. In terms of the exponential probability distribution, that's another one we can take a look at. Now I have a histogram over here. It's in the notes in the workbook. I don't have the code here. I simply want to say that there is an exponential probability distribution. We're not really going to focus on it much for this course. We're mainly going to focus on the normal distribution, but we will touch on it a few times. But it's f of x is equal to 1 over mu for the average times e to the power of negative x over mu. There is a package that you can use from Python. It's the Exponential package from scipy.stats, and we can import that to do the same types of analysis that we've done before. Now, if you follow the same steps, which are in the notes, you can always have expon.pbf from 0.01 to 0.99, break it up into X number of data points, and then just use expon.pdf to plot your point to get all of those PDF values. We've now arrived at the normal or Gaussian distribution. The normal probability distribution is called normal because it's a naturally occurring distribution that's affected by a population mean called mu and a standard deviation sigma through the following probability density function. So the function is stated as this over here. We have f of x is equal to 1 over sigma times the square root of 2 pi, and then times e to the power of negative, and then this term over here. So this is essentially a normal distribution. It's presented as a distribution with a true center. Wherever the data set center is, the mean, that's where the center of that of the peak is. And it's also has a skew coming from the standard deviation. So that skew is going to determine how tall it is and how squished or stretched the curve is. Specifically, what you should know are these two parameters. Mu being the average or the mean, it locates the center of the distribution. One of the requirements of a Gaussian distribution is that the distribution must be symmetric around the mean. So if I cut this in half, then that line that cuts the normal distribution in half is going to be the mean. Now, sigma is going to determine the shape of the distribution, the height and the width of this peak. If you have a large value of sigma, it's going to increase your spread, and therefore by increasing the spread, the height will also go down because it looks like there's more deviation to the curve. So how would we plot something like this? Well, we're going to use the norm package from scipy.stats, and we simply do the same thing as before. We have our x values going from a ppf of 0.01 to 0.99, just to keep things consistent, and then going to 100. Breaking it down into 100 points, we're going to plot the x values versus the PDF values for each of the x values. Now we're going to use mu and sigma in our parameters in this order so that we can plot the correct values for the PDF function. Once you show it, you'll be able to see the exact skew and as well as the center of the distribution for a normal Gaussian distribution. The other thing I wanted to mention is we can standardize a distribution. And what do we mean by standardize? It means that we want to force the mean to be at 0. Why? If we can force this curve to have a center at 0, it makes our calculations that much easier. So we standardize the distribution by forcing the mean to be 0 and by forcing the standard deviation to be 1. That means all the values on the right side are going to be positive and all the values on the left side are going to be negative. So let's take a look at how we can do this. So with the standardized normal distribution, any single normal distribution can be standardized simply by converting their values to z-scores. So we've already talked about z-scores. The z-scores essentially tell us how many standard deviations from the mean each value lies. So if we simply plot all of the z-scores, we'll be able to get a normal distribution that's centered at 0. So let's now call z the standardized normal random variable, very long name, but we can define it as the variable x minus the mean mu divided by the standard deviation sigma. We can rearrange this to solve for x, that equals to mu plus z times sigma. So this tells us a few things. It tells us that when our x values are less than mu, our z-score is going to be less than 0. When our x values are greater than mu, or greater than the mean, then our z-score is going to be greater than 0. But when our x values are equal to mu, then z is equal to 0. So that means right when the mean hits the center of your distribution, your z is going to be 0 because there is no deviation from the mean. So this curve right here is the exact same curve that I presented from before on the previous slide. So it's actually this one over here. But what I've done is I've taken out some, oops, let me go back here. I've taken out two different parameters from my code. It's these two over here, mu and sigma. If I add in a mu and I add in a sigma over here, it's going to force the distribution to be located at the true center, as well as have the true skew or shape of the distribution. If I take these two away, the norm function automatically standardizes your data set. So over here, how do we code this in Python? We simply remove the location is equal to mu and the scale parameters from norm.pdf. By doing that, the same graph that we have had before, the histogram gets centered over here, and then the probability distribution is now centered around 0. So that's what standardizing means. Once we have that, it's a lot easier to fit this model to different experiments. So just as a summary, what did we learn? In this chapter, we learned actually quite a bit of different concepts. We learned how to differentiate between discrete and continuous random variables. We definitely have to know what the difference is between PDF, PMF, and CDF. We learned about different ways of describing, plotting, and providing statistics for discrete probability distributions, specifically the uniform, binomial, and Poisson distributions. We did the same for continuous probability distributions, and we focused on the uniform, exponential, and the normal Gaussian distribution. And of course, we do want to understand how to standardize a normal distribution as well. So those were the key concepts from this chapter. Next, we're going to move on to additional statistics and additional measures we can do with probability distributions, and then go straight into statistics and data analysis afterwards.